Considerations of the total mechanical energy during uniform circular motion. Total mechanical energy. Right off the bat, that tells me that we're going to be looking at adding both potential energy and kinetic energy together to find out exactly what is going on. So, E mechanical will be equal to our potential energy mechanical plus our kinetic energy. I'm going to say that this potential energy is more specifically electric potential energy between a positive charge here and a negative charge going around the outer limits. Why? Because that's the way our atoms work. We've got the positive nucleus, negative electrons, so that's the reason for that specific consideration. The electric potential energy is K positive Q and the negative Q. And I'm going to have those be magnitudes and explicitly put the negative outside. Divided by the distance between them, R. Plus kinetic energy is 1/2 the mass that's going round and round, so that's the outer mass, the electron in this case, times v squared, how quickly it's whipping around the edges. Okay, that's half of our considerations. Next, the fact that this is uniform circular motion tells me that this negative charge, as it's going around, let's consider just a moment when it's moving along here with some speed, it's going to be pulled in via Coulomb's law, because we can approximate electrons and a nucleus as being spheres. The net force in this situation will be equal to the mass times the acceleration. The net force is going to be K Q1 Q2. Remember that second charge is negative. Boink. Divided by distance between them squared in the R direction. Note that this is a negative R direction inwards, which matches our picture. This is an inwards force situation. Mass times the acceleration. This is also a centripetal acceleration situation, which means that there's an inwards acceleration. That is v squared over R in the negative R direction. Let's simplify all this. Negative R hat, negative R hat. 1 order of R, 1 order of R. And we end up with mv squared is equal to k q magnitude of q over R. That is this. So we get negative k q q over R plus 1/2 of, doing a substitution here, k q magnitude of q over R. this and this are the same thing. When you add a half and subtract a whole, you end up with negative 1/2. So the total mechanical energy is going to be equal to negative 1/2 of the magnitude of your potential energy. Okay. The only thing that really needs to be taken the magnitude of is the outer charge, because that's the only thing that's negative. K is positive, capital Q is positive, R is always positive. It's just that little q, the charge of the negative mass, is negative. That's the only reason we need that. But a nice clean result. Okay, so there you have it. Based off of how far away masses are and charges are as they're in circular motion with each other, they have this much total mechanical energy. That includes their electric potential energy and their kinetic energy. That's it.